Okay, I wanted to clarify some of the concepts that we talked about in class today, specifically how to read the mathematics. I made a huge assumption. I am so sorry. I work very closely with exponentials in my own personal research, and so I wasn't seeing that y'all, I don't think we're following the mathematical relationships that the Clausius-Clapeyron gives us, because this is the linearized form of an exponential. So I was going to dive into the exponential idea to help clarify the relationship of heat of vaporization with the variations of the vapor pressure. So let's start with this picture. So we have vapor pressure is the pressure exerted by the gas particles above the liquid phase in an equilibrium. So if we add heat energy, so we add thermal energy to our system with our glorious PChem candle, we're adding thermal energy in, and not only is there a thermal expansion coefficient associated with the vapor, or sorry, associated with the liquid, but you're also going to be breaking some of those intermolecular interactions. And so the P vapor is proportional to the heat of vaporization, but it's not a direct proportionality, and that's where things get a little tricky. So one thing to think about is you've got two different scenarios of P vapor. You've got, so P vapor. So here you've got a very large vapor pressure. Here you have a very small vapor pressure. Notice it's really just the number of particles that are in the vapor phase, and there's going to be a higher pressure, higher force per unit area. Okay, so one of the things I want to talk about is the relationship. We'll get to this in a second. The relationship of P vapor is proportional to E to the minus delta H vaporization over RT. Now I am simplifying this a significant amount. You'll notice in Atkins that it says the Clapeyron, can't even say it. The Clapeyron equation is exact, whereas the Clausius-Clapeyron equation is an approximation. I'm approximating it even further by saying that this is proportional to E to the minus delta H vaporization over RT, and not multiplied by 1 over T minus 1 over T star. Okay, I'm just saying that this is approximately 1 over T. Cool, but it's for the purpose of the explanation. Okay. So it's really hard to relate directly the heat of vaporization and the vapor pressures from the linearized plot. Here, however, we have P vaporization is proportional to E to the minus delta H vaporization over RT. Let's focus here first, and then we'll relate it to P vapor. Okay, so this is a vaporization energy divided by the thermal energy that's available in your system. You can think of this as a pie chart, where this is delta H vape, and this is, I'm just going to call this delta RT, the change in the thermal energy that's available in the system. And again, I'm kind of incorporating in that 1 over T minus 1 over T. Okay, so if delta H is big, right, it takes up a significant proportion of our total energy that's available, because this is a fraction, it's part over the whole. So it would say that this is our delta RT, this chunk is our delta H vaporization. Or you could say, well, let's say the delta H vaporization is small. Delta H vaporization over RT. So it's a smaller value. Cool? So we have kind of two ideas. Big delta H vaporization, lots of energy necessary to break those intermolecular interactions. Small delta H vaporization, just a little bit of energy necessary to break those intermolecular interactions. Okay. If delta H is big, if this is a big number, that means E to the minus this big number is the same as 1 over E to the big number. That makes this number, so 1 over E to the big, this is not only big, this is just huge. So 1 over huge is equal to small. P vape equals small. So if it takes a lot of thermal energy to break those intermolecular interactions, the vapor pressure is going to be small. And I think that's where we had a disconnect, because I was trying to say that you could see that in this plot, but that's only if you're already thinking in terms of this is the logarithm and this is inverse temperature. And I'll get to that in a second, but it's thinking in terms of exponentials through the logarithm. And I was so sorry that it was clear that y'all weren't really following me. And you're like, yeah, I think I know what's going on. And y'all just, and it's cool. I'm so sorry that I didn't catch that. But this is the idea. If delta H is a big number, lots of energy necessary to break those intermolecular interactions, you're going to have this scenario because of this inverse exponential, which originates in the log proportional to the inverse temperature. Okay. Next, if this is very small, that means this is now 1 over e to the minus small number. Okay, e to the small number is still going to be big, but it's going to be smaller. Okay, so that would make 1 over small Pvap is now going to be bigger. And so if delta H of vaporization is very small, it doesn't take much energy to break the intermolecular interactions in order to vaporize it. This is going to be your higher likelihood. Okay, now let's convert that to the linearized form so you can kind of see the connection. All right, and herein lies the problem. These are not linear trends with the way that we think. This is inverse temperature. Okay, so not as clear. And so let me just give you some numbers. So I've got log of vaporization, log of P vaporization, or log of vapor pressure versus inverse temperature. And on my scale, 0.1, 0.2, 0.3, 0.4, 0.5. So from just 0.1 to 0.5. Here are the temperatures. This would be 10 degrees. This would be 5 degrees. This would be 3.33. This one would be 2.5. This one would be 2. So even though they look like they're ticks, they're not equivalent ticks. So you can't say, I'm going to look at this value to this value and say that I'm seeing a linear amount of energy that's going into my system times R. So if you want to think about how the slopes of these are affecting, so I was trying to relate this quantity minus delta H vape over R to the log of your vapor pressure. I wanted you to think about this as a scaling term to this delta 1 over T. And that's the part that's not linear. I mean, as you can see, these numbers are not easily scaled, but that's one of the reasons that we, plot it as 1 over T. And so by thinking about how this delta H vaporization, if this were a large number, now you're multiplying large number by an inverse of a large difference, thus making it a small value. Okay, so if you have this delta H vaporization is going to be, so back to the e to the minus delta H vape over RT, if this is a small number, this quantity then becomes 1 over e to a small number, making this whole thing big. Okay, so if this were a small number, you're multiplying a small number by a larger difference here to then make this a big number. So delta H vaporization is small is going to yield this to be a larger value because this quantity itself is the thing that's making it larger because it's 1 over that temperature difference. Okay, I hope that helped. But thinking in terms of the exponential, physically, I think it's more helpful, but extracting information is almost impossible from the exponential. You have to turn it to a linear form. But understanding this linearized form isn't equivalent to thinking in terms of, okay, heat in, vapor pressure goes up. which it does. If you increase the thermal energy in the system, the vapor pressure goes up. But don't forget, this is a constant. This is just a set value. There's only so much energy it takes to break those intermolecular interactions. So this is the thing that's temperature dependent. This is not. Okay. I hope that helped. So sorry for the confusion. Go team. Email with questions.